Right, good morning. So I want to start talking about classical diffusion, and we'll see that it is actually mostly understood in terms of random walk. I'm not going to get into too deep into details, but I want to just make sure everybody knows what it is, random walk. Yeah, that's kind of like a mystery to me. Nobody talks about probability, nobody talks about random walk, nobody talks about statistics, but we use it all the time, and it's always like a mystery. Why is it like we can do without it, or is it just like people don't care? So what we are going to do is so we are going to treat electrons like random walkers, and they are going to be okay. There is like periodic potential. We are going to like forget about periodic potential if you want by taking like an effective bandmass, but the random walk will be taking place from impurity to impurity. So electrons are going to bounce from impurities. And it is going to be like kind of like a chaotic motion. And what I want to at least spend today is to show that random walk, this kind of random walk, leads to diffusion. The more difficult problem, which is going to take a little bit more time, maybe next week, is to connect random walk or diffusion. So random walk and diffusion, they don't have any memory. Like as soon as you take your step, you forget about what you did. But quantum mechanics is not like that. Quantum mechanics has like phase, and electrons, they remember their phase. So we have to find a way to connect this memoryless motion to memory-full quantum mechanics, to quantum. But it is going to take some time. Like it is a little bit of, like I said last time, this is like a difficult problem, and we need to set up some like terminology first. Okay, now let's start with first, because we already have the ingredients for diffusion. I want to start with diffusion first. Let's introduce a density inhomogeneity, like I don't know, like something like that. I just like put like particles in a box, and then I put this kind of density modulation, and I expect that there will be like Fourier modes for each density. They are going to be time dependent, and we expect these Fourier modes to decay. This is rho of q of some 0 times e to the minus t over. They are going to decay with some like characteristic time, and here q is, I don't know, the characteristic distance of that the characteristic vector of this disturbance. But like there are like some constraints on this equilibration, right? For example, like if I were to look at rho of q is equal to 0, this is going to be, let's write, this is like Fourier transform, this is d cube r e to the I q dot r, but q I am taking is 0 times rho of r, but this is 1, right? So this thing is 1, and the integral of density over all space is going to be total number of particles. So that means there's like a constraint in that kind of equilibration, and the constraint is like tau of q should go to infinity, because right, something conserved cannot equilibrate. Like there's no like dynamics here. That means tau of q should go to infinity as q goes to 0, since n is conserved. And we can derive the necessary form from like previously we obtained so-called fixed law, and it was something like that. The current was equal to gradient of density, and there was like proportionality constant, and the proportionality constant was diffusion constant, the diffusion constant. Now there is like this conservation law. We can also put the continuity equation. If particle number is conserved, let's use like this. And here I want to substitute this j here, and that's going to give me del rho del t. This. Let me write this d on the other side, and there's like one gradient here, another gradient here. Is going to be gradient squared rho, and this is the diffusion equation. So this is diffusion. How many people know how to handle this equation? So, right? Right? Yeah. Yeah. So if you have never worked with this, no worries. This is like Schrödinger equation, right? There's no difference. The Schrödinger equation in imaginary time, if you want. Everything you know about Schrödinger equation, you can like dump it here. Now let's take Fourier transform. And Fourier transform in space, this is going to lead to del rho of q. Let me also put t. Del t is going to be equal to one nabla is going to give iq, a second one is going to give another one, and it's going to be minus d q squared rho of qt. And this is like trivial, right? First, there is nothing simpler than the first order differential equations, and the solution is going to be rho of qt is going to be rho of q0 times e to the minus t over tau of q. That's what we anticipated in the first place. And okay, maybe I do it in two steps. So if I do this, d q squared t, right? Because I'm just taking the integral of this and comparing this line with what we expected here is going to give us 1 over tau q is going to be equal to did I forget? Okay, that's good. D q squared. Okay, now let's try to relate this to random walk. So let's consider random walk. And I'll start with 1D, and it is going to be generalized to 2 and 3D trivially. So there, like in the random walk, there's like a step size s. I can take a step to the right, which is +1, and probability is 1/2, or I can take a step to the left, and probability is also 1/2. Then I can, like, for a given step, I can calculate the probability or like expectation value of this step. It's going to be value time. Okay, like, well, maybe I can write it like in a little bit form of appearance is going to be S PS sum over all S, and this is 1 times 1/2 minus this minus 1/2, this is 0. So this is mean, and I can also calculate the variance, and I can calculate like S squared, exactly the same thing, but this time 1 times 1 over 2, S squared is 1, plus minus a half squared is minus 1 squared is also 1, times a half is going to be 1. Then variance of S is going to be this minus this is going to be 1. So let's take n steps, and after n steps I'm going to be at the location xn, and expectation value of this can be calculated easily. Let me write it like this. I is equal to 1 to n Si, but like I said, this is like a memoryless motion. As soon as you take a step, you forget the previous step. That means this is going to be equal to, there is no cross correlations, I expectation value of S, and this is going to be 0. And similarly, xn squared is equal to I is I squared, and this is also sum over all I is I squared, but we already found this. Each one is 1 and there are n steps, so this is going to be n. So I have the mean at 0 and variance of order n. Then from central limit theorem, right, anything large enough is going to obey a central limit, which is going to be Gaussian, and the probability to be at a position x is going to be, the mean is at 0, the variance is 2 times n, right? That's the Gaussian, and the normalization is also trivial. It is going to be 2 pi n. Hopefully everybody knows that, right? As soon as you see variance and mean, you can write the Gaussian like this. Now, so this is 1D, like I want to generalize it to 3D space, and I want to also include time t, and for that x will go to r, and n is number of steps is going to be some constant times time, right? You take a step in every certain time interval, and this is going to be, like, let me copy this, and this is going to be something like that, p of r comma t is going to be r squared, so this is some alpha t, and I think this one is alpha t too. And so this was for 1D, and R is going to have X, Y, and Z components, so I just need to put one component for each, and R squared means R X squared plus Y squared plus Z squared.
Can you just repeat the n to time transmission?
Like the argument is like this, like, so I take a step in every time interval. Every 1 second I take a step, right? Then in really long time, number of steps I can take is proportional to amount of time I have available. And there is this alpha, at the moment we don't know, but we are going to relate it. So this is some microscopic quantity now, but we'll relate it in a little bit. So this thing, let me box in, I'll use it later. So the key about this is that in the random walk, expectation value of r squared is proportional to some constant times t. And so here d is d is equal to 1, 2, or 3 in dimensions. Now let's take so this is what we got from the random walk, and this is what we got from the diffusion. So diffusion is written in Q space, random walk is written in real space. Let's take the Fourier transform of this object and see how they compare. So this is P of Q and T is going to be d cube Q e to the I Q dot R times P R of T. And so this is just overall constant. And here R square, I can decompose it like X square, Y square, and Z square. I can decompose this is like QX, QY, and QZ. And there will be basically trivial Gaussian. You need to just complete the square.
So, is it integral over R?
Yes. So this is R. Thank you. Yes, I think I messed up here too. Yeah, this is a trivial Gaussian. If you don't know how to do it, just put it in Mathematica. It just gives you the result, but the result is like 1/2 Q squared alpha T. So I just put this expression to here, and I take the Gaussian integral. And comparing this line, PQ of T, with this line, right? There's like PQ and rho Q. I'm going to identify like P of Q and T. This is probability. I'm going to identify it with density of Q and T, and that's going to lead d Q squared T is equal to 1/2 Q squared alpha T, or I can raise this, I can raise that, then alpha is going to be 2D. Okay, let me write it. Alpha is going to be 2D.
So, rho Q0?
Rho Q0 is 1. Right, that's also, this identification requires rho Q0 to be 1. So when we, I'll talk about this a little bit if we have time, but when we derived diffusion, constant D, from Boltzmann, right? We didn't have to do that. Like we can derive diffusion. I think we can just from the start we can just go and write fixed law, right? It's like the law of the limit regime I'm studying, and I can continue like that. Or I can say Boltzmann transport actually describes everything, and then by manipulating the transport in some regime, I found the fixed law, and from that fixed law, we identified D to be 1/3 V Fermi squared times L times tau, or 1/3 V Fermi times L. So here tau is mean free time or collision time, and L is mean free path. Maybe I can write that. This is collision time. In Boltzmann transport, for example, we put like relaxation time approximation, and it was the characteristic time that things relax, or like this is sometimes mean free time. I think Gerwin Young calls this transport time. So this is mean free path. Then the diffusion is P of R comma T is equal to 1 over with this 2D alpha identification, 4 pi dt. This is e to d minus r squared 4 dt. And from here we see that expectation value of r is 0, whereas expectation value of r square is 2 dt, right? Standard Gaussian. or actually like this is x square, y square, z square, right? And for each dimension I need to put 1, so this is going to be 2 dt times d actually, to be more precise. And the picture is so this is R, this is P. I have this Gaussian distribution and it relaxes with this 2 dt.
So where did you place d in the previous equation?
So it's d.
No, it's small, lowercase one.
So this one. So this one comes from like this. So this r square is x squared plus y squared plus z squared, and each one is going to be x squared plus y squared, right? And each one is a Gaussian, so each one will come with 2 dt. If I have 1d, there's one of them, 2 d2, and so on. Yeah, that's a good point. But let's. I think I want to spend like maybe 10, 15 minutes to talk about random walk, because most physics students never see about that. So let's consider microscopics. Microscopically, electrons bump of impurities, and the picture is something like so there's like crystal lattice. Like I said, crystal lattice doesn't do anything, right? This is Bloch waves. Bloch waves just go without any scattering, and I have some randomly located impurities, something like that, and my electron, I don't know, goes from one impurity to another, something like that. And this entire motion is described by some mean free time or collision time. So this is time, or there's a corresponding L is equal to electrons. There's only one velocity for electrons, and it's the Fermi velocity. V Fermi times tau is going to give you mean free path. So these are the microscopic quantities, and we want to calculate other things in terms of this. So first, let's try to calculate average time for collision. Average time for a collision. So how long does it take on average to have at least one collision? And of course, like the idea is, if I spend very little time, right? If my time window is like very small, I shouldn't have any collisions. And if my time window is so big, it's close to relaxation time, I have to have collision for 100%. Then the collision time is going to be proportional to this delta t over t, right? However, how long I have is going to be proportional to probability to collide or not. And now let's think about this. So here is my time window. So this is time. So this is 0, and this is some t. And I want to calculate probability to have a collision in this window. What I want to do is, like, I want to use this, right? For small times, I know this, but for longer times, I need to relate this to here. I just divide this into smaller intervals, dot, dot, dot. And each one is delta t. So this is delta t, dot, 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 delta t. So now, so this is a little bit of different p. Let me use, so this is different probability. Earlier probability was something else. So now, not to use too many letters, I use the same thing. So this is probability to have a collision at time t is like probability to have no collision here, no collision here, no collision here, all the way to no collision here, right? And then you collide here. Then this is going to amount to the probability to have collisions delta t over tau. Then not to have it is delta t over tau. 1, one more for the second interval, t over tau, dot dot dot, all the way to 1 minus delta t over tau.
Can you explain delta t over tau?
So here is actually, yeah, this is really like simple, right? So I have like some characteristic time that I have a collision, right? I'm saying that I don't know what it is, but there is like some typical time. And how is this related to my collision probability? So if I have very little time, right? If delta t is very small, I should not have a collision, right? So, and if I have delta t is equal to this characteristic time, I have to have 100% collision. Then from here I like set up this form. This satisfies the condition. If delta t is tau, I have 1, probability is 1. If delta t is equal to 0, I have 0 probability. And here this delta t is equal to t over n. And this is trivial, right? This is 1 minus t over tau divided by n. So I wrote this t over n, and I combined this t over tau like this. And this is to the power n. And as n goes to infinity, this is going to go to minus t over tau, right? Everybody knows this. I don't think anybody has any problem with this. And so if this is the probability, I need to normalize from 0 to, so 1 should be equal to, if you sum over all, so this should be 1, and this is going to give me, the normalized p is going to be 1 over tau e to the minus t over tau. And now I can calculate collision time or mean free time, right? Like there are many things this is called, and we have to remember what we mean. And this is expectation value of t under this probability. And if you put that in here, you are going to just find tau, right? It just makes sense. You just close the loop. You got what you expected. There's also something called mean square time, and this is going to be t squared. And if you put it and then calculate the integral, what you are going to find is 2 tau squared. Gerwin Young says that Drude, when he did his calculation, he missed this factor of 2, but I think it's not important. So there is like mean square length. This is shown with delta squared, and it's going to be V Fermi tau squared expectation value, and V Fermi is a constant of this theory, so it's going to be 2 V Fermi squared, and expectation value of tau squared is 2 tau squared. And I can also write this in terms of L. L was equal to V Fermi times tau, and it is going to be 2 L squared. So mean square length is 2L squared. Okay, so why do I do all of this? So I want to eventually find D, the diffusion constant, without referring to the Boltzmann equation, and with only using like simple probabilistic interpretation, or like simple probabilistic picture. Now I have to do one last thing. I need to ask, what is the average number of collisions in a given interval t, in t. Again, let me write this. So this is time, so this is 0, this is t, and I divide this dot dot dot. So I need to write a probability for n, right? And here I am saying that between 0 and t, suppose I have n collisions, and here I have n intervals. Then that means I have to put little n collisions to big N intervals, right? That's like a combinatorics problem. And I can write it like, okay, this is yet another probability. This is also different, but not to collude the workspace. I'll use P all the time. From the context, we know what it is. Different from P of T and different from P of R of T. So this is collision probability. And this depends on N. So first, the combinatorics factor, right? I need to distribute N collisions to N intervals, and this is going to be N factorial divided by N factorial N minus N factorial. Yes, standard combinatorics factor. And in N of these intervals, I have a collision. That means this is going to be delta T over tau to the N. These are the collision probabilities. And in N minus, big N minus N of these, I have to have no collisions. So this is going to be 1 minus delta T over tau to the power N minus N. And I want to take the limit and it goes to infinity and find this probability distribution. Yes, it is going to be Poisson, but I think yes, if you didn't know this, that's where it comes from. But so this is going. The way I want to do this is like this is n minus 1 dot 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 n minus n minus 1, and the factorial 1 here is going to cancel that, and in the denominator I'm going to have n factorial. So here this delta t I like to put here t over n and take this n outside. So this is 1 over n to the n.
So the last term is plus 1.
This one?
No, the denominator.
Oh yes, this one.
Yeah.
Okay, thank you. Yes, because we cancelled. Yes, correct. And this one is t over tau to the n. So this, now I wrote this term, and the second term is going to be 1 minus t over tau over n to the n divided by exactly the same thing, 1 minus t over tau to the n to the power n, right? So this last one is this one, right? And this thing is this, and this thing is this. Now as I take n goes to infinity, there will be factors of n here, this one, and this one. They are all going to cancel, right? They are all going to be 1. Then this is going to be 1 over n factorial. This is going to be t over tau to the n. And so as n goes to infinity, right? So this, okay, the limit is this big N goes to infinity. So this thing is going to go to 0 because n is like very large. And there's only this one, but this is also the exponential as n goes to infinity. This is minus t over tau, right? That's clear. And that's the, exactly like you said, that's the Poisson distribution. Then I can calculate mean value of collisions, right? That's like standard, just plug it in and look at the power series of exponential. It's like trivial. Let me just write the result. What you are going to find is t over tau, right? So the number of collisions you get is proportional to your time, right? And it is, right, total time divided by tau, and it is your mean number of collisions. I can also calculate now r squared. And what we said is like this is kind of like a random. This is a random walk, and as soon as you take a step, you forget the previous step. That means this is going to be the average number of steps times mean square of each step, right? Because each step is independent, so I just can write this as total the expected number of steps times mean square of each step. Now let me so I calculated this, I calculate this, so let's plug in. So this is going to be t over tau, and this is delta squared. We found this to be 2 v Fermi squared times tau squared, and this is going to give us 2t v Fermi squared times tau. And that's the end of the calculation. So in the diffusion equation, what did we find? We found r square was equal to 2dt times t, and we equate, right? One comes from diffusion equation, the other one comes from random walk. If we say they are supposed to be the same, what we find is 2dt d is equal to 2t v Fermi squared tau. Cancel this, cancel 2's, and what I find is this is 1 over d, and in in 1d this is 1 into the, okay, let me write this. So this is d, d is equal to 1, 2 or 3. And lastly, let me write this diffusion one more time. This is P of R of T. Now we can forget all these intermediate P's we introduced. This is the first one we introduced, and it was equal to 1 over 4 pi dt e to the minus R squared to the t. So, and in d dimension, this is going to be d, and here d is given by this. Yes, you are right. This is 40. Yes. And for example, I can calculate return probability is after you start at r is equal to 0, and after a while you come back to r is equal to 0 at time t. So this is p of 0t. It's going to be, if you put r is equal to 0 here, this term will vanish, and what you are going to have is 4 pi dt d. Let's actually calculate, because we have time, and let's calculate probability at some point in time, probability return to the origin, right? That I ask, so what is the probability to return to origin at some time from t is equal to 0 to infinity. And I can use this, so it is going to be but like okay, let me first write it and then modify. So this is this guy, and this is dt. So I need to integrate this from infinity, but for us to make sense of diffusion, right, the time is not going to start from 0, right? For diffusion starts from like a characteristic time tau and above. And now this one is 1 over 4 pi d, and so this is going to be, I think I like to do this in this dimension, but let me try and see if it works. So this is going to be t to d minus d over 2 plus 1, let me take it one by one, right? This is like d is equal to 1, so this is 1 over root t. I need to integrate. It is going to be 2 times root t in 1d. In 2d, it is going to be 1 over 4 pi d. D is equal to 2. This is going to be log of t. And yeah, I will put the limits first. I'll take the integral at this. I'm not confused myself. So this is going to 1 over 4 pi d, and this is 1 over t to the 3 over 2. If I take the integral, it is going to be 1/2 and something like that, right? If I take 1/2, maybe minus, and now put the limits from tau to infinity, from tau to infinity, and from tau to infinity. So what this says to us is like, as you can see, in one, so this is 1D, 2D, and 3D. So as I put infinity here, so this probability, so this is return probability is equal to, in 1D this is infinity, in 2D it is also infinity, right? But it is not like as bad as this infinity. Like some infinities are worse than other infinities. So this is like logarithmic infinity if you want, but still infinity. But in 3D we have, if you put this, there's also this minus. Okay, this is 1. Okay, there is some, let me write it, 1 over 4 pi d, 1/2 root tau. So this is 2D, this is 3D. So this is finite. And this exercise proves that in 1D and 2D, you are guaranteed to return to origin, right? So that's the thing about random walk. If you are lost, you just keep walking, right? If you don't know the city, at some point you are going to return to where you've been, because we are walking in a two-dimensional space in the city. But in 3D, that's not the case. In 3D, you can just really get lost. And we'll see that this behavior is going to lead to localization, because if you are returning to where you are, there is like a very special case, right? Now, electrons, we said, are like random walkers, but they are not random walkers. They have phase, and if you are guaranteed to return to where you started, there's a very special form of interference, and that interference is going to lead us to localization. But for the moment, we only know classical diffusion, and classical diffusion tells us that in 1D and 2D, it is a little bit different from 3D. Okay, any questions? Okay, thank you.